talked about this joke. Right now, you'll chuckle on it, but it'll make more sense when we get there, okay? So this is chemistry. This is chapter 2. I'm going to do the general chemistry first, give you guys a little break, and then I'm going to do the organic chemistry, and that's doing about lipids and carbohydrates, sugars, and stuff. And that will, and then we'll be done with that, okay? And whatever time we have left, I'll just go over some skin stuff, just pointers kind of thing. Not much, because it really is a lot of layers, a lot of memorization. There isn't much physiology in skin, except maybe wound healing. But you really could do it on your own. It's like, it's self-explanatory. So, but I'll give you some pointers on it. All right, so chemistry. So, I'm not a big fan of chemistry. You have to understand that, okay? I don't like chemistry, but I can't get away from it because it is the basis of us. So that's why we're doing chemistry. So why chemistry? It is the basis that builds all of us up. So we have to talk a little bit about it for you to actually appreciate this stuff. This is I'm going to give you the meat and throw out the fat and gristle. When you take chemistry, that's where you'll get it. You'll never see me teach chemistry, a full course. I'm only giving you the meat over here that you're going to use for A and P, okay? So I promise, it'll just be the mere basics. Doesn't it feel good? We just knocked off 3 slides, okay? All right, so the best way to start off is matter, okay? What is matter? It's anything that will take up space, anything that has mass. You yourself are taking up space in this room, so you have to be some sort of matter, all right? So it could be some liquid, okay, or solid, right? So you could also be a liquid over here, or gas. Anything that's gonna occupy space. I'm gonna turn off these lights a little bit. All right, anything that occupies space, solid, liquid, or gas. Okay? Mass is the measure of how much space an object takes up. Okay? That's what mass is. So, do you weigh the same here on Earth as you do on the moon?
No.
No.
Right. But you have the same mass on the moon and the Earth, but you don't weigh the same. So what I want to explain to you is that mass is not the same thing as weight. When you deal with weight, we're dealing with gravitational force. Since the moon is smaller, you're not going to be pulled down to this core of the moon as much as you would on the Earth. I went to the Museum of Natural History, I think last summer or something, and what's really neat about it is that they have the moon over there, the planetarium kind of stuff, and there's a scale that you could stand on. You go on the scale and it kind of tells you how much you would weigh on the moon. I weigh 26 pounds. I'm moving to the moon. I don't even want to tell you what it's like. Okay? So mass versus weight. Mass is a measure of matter. Okay? You're still occupying the same amount of space whether you're here or you're over on the moon. Okay? So the mass is still going to be the same. Okay? The weight, you have to incorporate the gravitational pull. God bless you. You have to incorporate that, okay? The Earth is huge, so it's going to, pull you down further, so it's going to create weight. If we were on Jupiter, the largest planet in our solar system, we will weigh a lot more. You won't find me on Jupiter. I don't want to be weighing, let's say, 1,000 pounds for that reason, okay? So that's what that is, all right? And I can't really explain this, but just to let you know that the way that the Earth is, it's a little flatter on the North Pole and flatter on the South Pole. And basically, you weigh a little bit less when you get to the North Pole. Okay, not much, like maybe a pound. It's not going to make me go up there. I guess that's why Santa Claus is up there, because he's so big and it looks on the scale.
That's a good way to look at it.
Yeah, you can look at it like that. Okay. All right. So we have states of matter. We have solid, liquid, and gas, right? These are the ones that we've learned about from kindergarten and stuff. There is a fourth one called plasma, okay? And it's not the same plasma that I talked about that's in blood. This is plasma. And plasma, I guess it's like the plasma screens. It's a liquid, but it's not it's that kind of story. All right, we see a lot of this plasma also in neon signs and stuff. I just want to let you know that that's there. Put in parentheses because it really has nothing to do with anatomy and physiology. It doesn't really incorporate that. But I don't want you to go into chemistry, a chemistry course, and they talk about the 4 states of matter, and like Dr. Gamarl just talked about 3. Does he really know everything what's going on? There is a 4th one, which just not really dealing with A and P, okay? So solid, basically I'm going to do these very fast because you learned this kind of stuff earlier. It has a definite shape and it occupies a definite volume, okay? That's what a solid is. Liquid, there's no definite shape, right? You spill milk, it goes all over the place, but it still occupies a definite volume, okay? And then a gas, there's no definite shape, there's no definite volume. It just gets scattered all over in the sky, all right? So that's what the 3 are. So we got to talk a little bit about energy. Energy is when matter can do work, okay? So we're putting matter into motion. And we have 2 types of energy. We have kinetic energy, and that's energy that's moving. So like the slinky over here, as it's moving, that's kinetic energy, all right? Or if you have, let's say, an elastic band, if you stretch it as far as you want, let it go. As it goes, it's kinetic energy, okay? And it's going to release energy, heat usually. You do that enough, heat will come off of that. Then we also have potential energy. This is stored energy. This is energy, if I take this rubber band and I stretch it and I hold it like that, that's potential. It has the potential of becoming kinetic when I let go of it, okay? So we have kinetic energy that's moving, and then potential energy that's not going to give off anything, but it has the potential of becoming kinetic if it has that will to do that, okay? So matter can change state, right? Matter can change from one state to another. A solid can turn into a liquid, can turn into a gas. Again, I think you've learned this from kindergarten, right? It requires some kind of addition of energy. Hey, I got an ice block over here. I'm going to put heat to it, energy, and it turns into a liquid. I put heat to it, it evaporates, right? So if you have to, in order for it to go from a solid to a liquid to gas, you have to put some kind of energy to it. If you subtract energy, the opposite, then it go the other way. You know, I'm going to put it in a freezer. Freezer doesn't have much energy. It's going to turn into ice. All right? So that's what that is. Now, state changes. These I think you know about. Evaporation, liquid to a gas. Condensation, a gas to a liquid. Okay? Freezing, liquid to a solid, and melting, solid to a liquid. Pretty straightforward. But we have 2 other ones you probably don't realize. Okay? And what we have is deposition. Deposition is skipping the liquid state, and it's going to go from a gas to a solid. This is turning carbon dioxide into dry ice. Dry ice is, you ever see like the haunted mansions, the smoke that comes out? Well, it's from this dry ice, which is, I wouldn't say dry, solid carbon dioxide. To make it, you have to do deposition. The opposite of this is sublimation. This is the stuff you do see at the haunted mansions. When it's going, you know, you have this block of dry ice, they call it dry ice, but it's solid carbon dioxide gas. And what it does, it's solid, and it actually will turn into a gas immediately. And that's what that smoke that you see at the haunted mansions. So you have deposition and sublimation. So again, it skips the liquid state. All right, now let's talk about atoms and bonds. Atoms turn into elements. Elements will turn into molecules. So an atom is the smallest thing anything can be broken down into. You can't even see this. I don't even think we have techniques that you could actually see this. Okay? So more or less, they're identical building blocks for each element. All right? An element is the simplest type of matter that has unique features of that chemical. In other words, a gold atom and another gold atom. You put them together, you're going to have elements. They all have this. You can't put a silver and a gold atom together. That is not an element. Those are two different elements. But if you have atoms that look alike and have the same features, then we're going to call it the gold atom. And when you put them all together, that's going to be our element. One atom, or many of the same atoms, are going to make elements. A molecule is made up of two or more of either the same or different elements. So, what we have over here is that if I have oxygen is abbreviated with an O, and I can put maybe two H's over here, hydrogens. That's a molecule, okay? I could also do an oxygen molecule is like this, and sometimes put double bonds, and we'll talk about bonds in a moment. So this is a molecule, and this is a molecule. This is a molecule with different elements. Here's a molecule with the same elements. So molecules have either the same or different elements. So like I said, this O stands for oxygen, H stands for hydrogen. There's a lot of other ones out there. I'm not going to ask you to memorize all those other ones, just the ones that we're going to use quite often. And you're going to see them as we go along. I can't say what's the list of them. As we go along, you'll learn all about those. Okay? We don't have to worry about boron. Boron is not going to be really relevant when we deal with, let's say, anatomy and physiology. But things like oxygen and carbon is over here. Sodium is Na. You would think why isn't it SO? Because it's Latin. Natremia. And that's that's what sodium was before the English language came in and called it sodium. Okay? So we have little symbols for certain ones on here. Compounds are made up of two or more, but they have to be different elements. So, this is a molecule, and this is a molecule. This is a compound, this is not a compound. Do you see why? They have different elements here, but they're the same over here. It's more semantics. I find a lot of students, including myself, we call it molecules and compounds being the same thing, but in actuality, we'd be wrong into doing something like that. I would probably get penalized by chemistry, because they're so prim and proper. They got to do it the proper way. You know what I'm saying? It's like, what do you mean? You don't know. I'm just saying there is a difference between the two. Okay? We got carbon dioxide, which is a carbon and oxygen. Here's water, H2, because there's two hydrogens. And here's sodium chloride. So these are examples of compounds and molecules. So we can say all molecules are compounds, but not all compounds are molecules, right? These are the four most abundant chemicals in our body, elements in our body, okay? Carbon, hydrogen, oxygen, and nitrogen. Now, when I was in when I was in high school and I took biology for the first time, my biology teacher's name was Mr. Seishon. And he told us, I don't even know if he's still alive now, but he told us, he said, you'll always remember his name because the last four letters of his name are very important. And to this day, I still remember it. So, these kind of things kind of stick with you. Okay? So these are the most abundant things. Iron. You would think that we've got a lot of iron in our body, but it's like about 1% of our body. It's very, very low. Okay? Bless you. But we have so much of this other stuff in our body.
Is that in order? Is carbon the highest?
No, it's in order of my abbreviation.
Okay.
Yeah. Or my anatomy. God bless you. All right. So what is an atom? Let's talk about what an atom is. An atom has three subatomic parts. There's going to be a proton, a neutron, and an electron. In the core, the nucleus over here, we're going to find protons and we're going to find neutrons. Okay? Then we're going to have electrons, which is going to be the smallest of the three, and they will go around. They actually move all the way around here in things called orbits or shells. Okay? They float around here and they move around. all right, kind of like this, and I'm sure you've seen something like this. And each one of these shells has names to it, where the electron is. There's something called 2ps, a 1ps, a 1d, and all that stuff. I'm not going to go into that. I don't think it's really relevant to understand that. I think what's relevant is understanding what's a charge. Why is there a positive charge or negative charge? And I don't think, at least the way I teach it, I don't think you need to know the names of the shells to understand that. You'll see what I'm saying when we get to this. All right? Now, when we deal with charges, proton has a positive charge. A neutron has no charge. And the electron has, well, you're going to have to figure that one out. All right? All right? So, but if you know the other two, you'll be fine. But electron has a negative charge. These charges are important to understand about when I put sodium has a positive charge and chloride has a negative charge, where are these charges coming from? And the one that's going to be responsible for the charges is going to be our wonderful electron. Now, before we talk about the charges, let's just talk about the numbers of these protons and electrons and stuff. The atom nucleus has protons and neutrons. Atoms are classified by the proton number, okay? Changing the number of protons means we're creating a whole new element. Like hydrogen only has one proton, all right? Helium has two protons. If you take a hydrogen and you want to put another proton on there, it's not hydrogen anymore. Now it's helium. So the proton number is going to determine what element this is.
I just said that again.
I'm going to show you a picture so you see it on here, okay? The neutrons, normally you're supposed to have the number of protons equal the number of electrons equal the number of neutrons. That's a stable element. However, the neutron number may change. The proton number can never change. Because like I said, the proton determines what element that is, not the neutron, not the electron. So here, this will make sense a little bit more. Here's hydrogen. The red is actually symbolizing a proton. The gray or the black is going to represent an electron. So in a hydrogen, you're going to have one proton. In helium, you'll have two red over here. In lithium, you'll have three red in here. The red protons are determining what element that is, not the neutrons. Like here, you don't have a neutron here. You may have a neutron here. You might have two neutrons there. It'll still be hydrogen because there is only one red proton. So that's what I want to say, is the proton determines what element this is. But you could change the neutron. And you could change the electrons for that, okay? Isotopes. Isotopes is if the neutron changes, but the proton number has to stay the same, otherwise you're changing the whole creature now. But if the neutron changes, that's what an isotope is. Changing the number of neutrons is the basis of nuclear chemistry, which is important for radiography. And I don't want to get into too much of that because you'll spend more time talking about isotopes and how to apply this stuff when you get into your chemistry course. But just understand that, I want you to know what an isotope is, just a basic understanding, so that when you take chemistry, when you go into radiography, if that's what you're going to do, then that means you have a little bit of understanding about this. All isotopes of one element react the same way because they have the same number of electrons. Okay? For instance, oxygen has 8 different isotopes, meaning they have 8 ways it could look like itself, but it just has a different number of neutrons. But each of those will function the same way. It just looks like a different creature. Okay? All of us are humans. We all look different, but we still all function the same way. Okay? Now, isotopes can be stable or they could be unstable. A radioactive isotope is an unstable isotope. It's it's reaching to become stable. But right now it's just unstable. And what this is that the atom's nucleus will decompose until it finds a way to get to a stable position. As in the process of it trying to find that stable position, it's going to release energy. This energy is radioactive, things like gamma rays, and this could be measured. It's used clinically for imaging, for radiography, could track hormones. We could attach it to certain hormones and see where it goes, and we can see on the screen what it looks like. It can also be used for treating cancers. They got to get radiotherapy, because some of this is really dangerous. You've learned that right in kindergarten too, like radioactive. Oh no, you got all superheroes like Incredible Hulk and stuff like that, were radioactive, and see what happens, right? So that's what we use this for. It's a medicine. The radioactivity is a medicine. You don't want to have that. You want it to kill the cancer, but you don't want it to kill your good cells too. So you got to make sure you give the right dose of this and how much you're going to give. Okay? So that's what this is all about. Isotopes is dealing with this stuff. So that's about as much as I want to talk about with isotopes. It gives you a little understanding, because we always have a handful of students that are going for radiography, so you should have some understanding what this is all about. Okay? So here's 3 isotopes of hydrogen. It's hydrogen because there's only one proton. There's only one red ball in each one of these. That's hydrogen, and that's hydrogen. But this has no neutron. This one has 1, this has 2. It's still in the realm of hydrogen. It's just that we have 3 different isotopes that hydrogen can stand in. Okay? And that's why that is. Okay? Now, let's talk about definitions. The atomic number tells us how many protons is there. Very easy, okay? Give you atomic number, you know exactly how many protons are there. There's something called a mass number. That's when we add up all the protons and all the neutrons. That's the mass number. The atomic weight is the average of all the mass numbers in all the isotopes. So if we go back to this one, there's a mass number here, there's a mass number here, there's a mass number here. And what we're going to say is atomic weight is the average of those 3 mass numbers. So we could do a little bit of algebra over here, and we could say that to get the number of neutrons, we can, if we know the mass number and the atomic number, we could figure that out. So if I give you, let's say, a mass number and atomic number, you can tell me how many neutrons that particular atom has. Now, I am not going to test you or give you a periodic table on here. All right? I think most of you have seen this. Most of you got headaches from this. Take chemistry and you'll learn more about this. There is a way, and it's been a while, but there is a way where this whole periodic table with all the elements in the world, let alone probably the universe, it's very organized in a way. They have different colors here that, this is like the, like we have the noble gases over here, we have the metals over here. There's all these kinds of things, the reason why they're shaped like this table. Okay? I'm not going to ask you about this, you don't have to worry about it, but I do want you to, most of you have seen something like this, but I do want to show you the stuff that we did just go over. It's found on this. For instance, the atomic number is right there. Every periodic table will have these 3 basic things. The atomic number, there's your hydrogen 1, lithium is 3, helium is up here is 2, okay? The atomic weight, which is the average of all the mass numbers of the isotopes, is also there too. You don't have to calculate that. They're all there. And of course, the chemical symbol would all be in there too. All right? Not going to ask you about that, but if I'm trying to bridge your chemistry course from before or something you're going to take later on, it's there. Okay? All right, now let's talk about ions. An ion is going to deal with electrons. All right? Now you have to keep in mind, for you to understand this, that an electron has a negative charge. And what I'm going to show you will make more sense. It has a negative charge. So an ion is an atom that either has lost or gained an electron. An electron is negative. So we have a cation. That is positive. It's when an atom loses one or more electrons. It becomes positive. That's where a lot of students say, whoa, is that a typo? If you lose something, why am I positive? You see? It's because the electron's negative. I'm going to show you up on the board and it'll make more sense of it. We call it a cation, a happy cat. Okay? Or a cat has a T